Hello everyone, we are again together for a new lecture which is main free path. Today we will discuss the main free path in detail by taking some example and some relation and which relate to the main free path. In this lecture we will discuss the content of lecture firstly which is introduction of main free path. We will discuss the definition of main free path and other uh, things which related to the main free path. Then we also discuss the equation for free path, how we can find the main free path from the equation. So at lastly we will also discuss the relation between the main free path and collision frequency, absolute temperature and other terms. So firstly, we start from the main free path. Main free path actually when gaseous molecule travel in a straight line during successive collision, the direction of motion get changed after each collision, resulting zigzag motion. You can see in the picture. After collision, the molecule collide and then they travel some distance which is denoted by L1, L2, and L3. And after the collision, they can move or change their direction by zigzag motion. You can see in the picture, after the collision the gas molecule move zigzag motion, and for each collision they need to travel some distance. So we denote this distance for, which is L1, L2, L3 up to Ln. After before collision, these are path length we can, and the molecule can be travel from, and their velocity is Ca average velocity, then Z is the collision frequency, which is number of collision per second. And further we have some relation for the total free path distance traveled, which is L1 plus L2 plus L3 up to Ln. Similarly, we can you can see that the total free path traveled, which is equal to Ca into T. When time is 1 second, then it is equal to the average velocity. So the now main free path is equal to average free path, and or you can see that the total free path in unit time divided by number of collision made by the molecule in unit time, or we can write in mathematical relation L1 plus L2 plus L3 up to Ln divided by Z. And Ca, which is equal to L1 plus L2 L3 up to Ln, which is equal to Ca, and Z is a collision frequency. So we can write this equation into that form, Ca divided by Z. So we already know that substituting the value of Z, we already know the value of Z, which is equal to n2 under root pi sigma square Can in equation 1. Then the main free path is equal to, where sigma is a collision diameter and n is the number of gaseous molecule per volume per centimeter cube. Or we can write this equation into that simplified form, 1 over n 2 under root pi sigma square Can. From equation 2, it is evident that the free path is equal to is directly proportion inversely proportional to the sigma square, and also inversely proportional to the molar mass of a gas, and also inversely proportional to the sigma square, which is collision diameter. So if collision diameter is more, then the molecular volume is more. Hence lesser time is needed for the collision, leading to short path length. Likely if n is more, then collision is fast. Hence L free path is shorter. Further, it is a number of molar mass is directly proportional to the pressure of a gas. Hence, the pressure is high, then shorter will be the path length. So this is a relation about the main free path with the other term. So the further we will discuss the dependence of free path, which is denoted by lambda on the pressure and temperature according to ideal gas equation. PV is equal to nRT. Then we have to replace the n, which is with molar mass and small n and Avogadro number. So we can write PV is equal to n over NaRT. And then n, if we find the n, which is equal to na v over r into p divided by t, where n is a total number of gas molecule, p is a pressure exhaust by a gas, n is a Avogadro number, r is a general gas constant, and t is a absolute temperature. So we can write this equation, which is equal to k dot p over T, because K is equal to NAV over R. So on substituting the value of number of mole N in equation 2, then the main free path, which is equal to lambda is equal to 1 multiplied by T divided by 2 under root pi sigma square K dot P. Thus the lambda directly proportional with the temperature, and which is also inversely proportional with the pressure. So the under the same condition of temperature and pressure, the n remains same for the different gas is per Avogadro law, and the diameter of molecule of a different gas is generally for same order, 10 to 8 centimeters. So the lambda also remain of the same order. Therefore, under the same external condition of main free path of various gases will be of the same order. Thank you for watching. We will together again for a new session. And here we have to leave our this session. Fi Amanillah.